So next up is Sauro on decision support tools for planetary exploration using bespoke databases and machine learning.
Thank you. So this talk is also in the frame of the Pangea program of the European Space Agency. And I will present how we can use mineralogical databases and machine learning for providing pre-digested data from the field to science spectrums for decision support. Next. So the use of portable analytical tools in future Artemis missions will be surely a major advance compared to Apollo times. If data on potential sample is available immediately, and the science spectrum really can provide advices and target the most relevant samples for science. Next. In the Pangea training and program, we try to address this question on how data can be used for supporting decision making, because it is a very different context compared to, for example, Mars rover missions, where there is a reasonable time for analysis of raw data. Here we could have a huge amount of data coming, and how we can use this data to really make it a decision making tool. So we focus on how we can have efficient recognition of minerals and the chemical composition on the fly. Next. So of course, there are three main elements in this approach. We need handheld spectrometers, and I will not talk specifically about that. But also we need mineral recognition softwares using artificial intelligence or machine learning. And we need also mineralogical databases, because we need the spectra, for example, for matching what we achieved on the field. Next. So first of all, we try to develop the databases, and it's a project that we are running since many years. It's the Pangea Mineralogy Database. It's now available to everybody on Mendeley. And this database is based on bibliographic research, of course, and it's a catalog on all currently known minerals on Moon and Mars and meteorites. We have over 1,000 minerals, which have also associated spectra for different methods like Raman, VNR, and LIBS. Next. So with this database, of course, we can then target mineral identification, but there are many different methods that can be used also with portable tools. We can have molecular spectroscopy that gives information about the minerals themselves, like Raman or VNR. We have elemental spectroscopy that gives information about the composition. So all this data has to be integrated. Next. The library which is associated to the database, especially the VNR and Raman spectra, are collected from databases. So the existing databases like USGS, RUF, for example. And we have also done our own measurements in collaboration with several museums, for example, collections and institutions from the academy. And we have now 10,000 high-quality Raman and VNR spectra. Next. Also, we need, of course, to validate this data, because we need to remove baseline, for example, interpolate spectra for the same linear resolution range. And if we have been developing our own pre-processing software that allows all of that, and we can also normalize the spectra to then be used by different instruments, and also allowing to remove outliers. Next. So, and here, when we have a database like this, we can really start to use the machine learning. Machine learning has a lot of benefits, can really quickly match the spectra with the one that we get from the instrument. We can handle a multi-variety of data, and it's also self-learning with new data. It has also some drawbacks, like it requires massive data sets and needs to teach algorithms. Next. So this approach has been used, of course, also by the industry for analytical tools. But what we try to do is to use it for data fusion from different methods. So imagine that you have analytical tools that combine two methods, like, for example, Libs and Raman, so molecular and compositional spectroscopy methods. So we get the composition, but also the structure. If we merge this information through machine learning, then we can have a much better recognition of the mineral. Next. So the work has been done also trying to improve the current state of the art. We have been developing our a specific deep convolutional neural network solution. And then we have tried to verify if this approach works well with, for example, Raman plus Veneer, Raman plus Libs, or Veneer plus Libs. And we recently published a paper that shows that with this approach, we can really increase the accuracy of recognition. So we can have from only Raman, for example, is 85% in known methods. Veneer is even less. But combining these two methods, we can reach an accuracy of over 90%, which is really, really good because we can really get an answer very quickly and a very precise answer. Next. So now the challenge is that we are talking about recognizing minerals, but a single mineral. But of course, when we are dealing with rocks, we have mineral mixtures, and what we will see on the moon with these instruments are spectra, which are a combination of different minerals. So as we have been going through multi-class classification and multi-method classification, now we are working on multi-label classification. So identifying components of the same rock and having an answer of not just if we have a specific mineral, but how many and different minerals we have in the same spectrum. Next. So all of this, imagine that all of this is coming from the field and goes through a system that integrates all this information. So it really processes on the fly all this information through the mineralogical database, the spectral libraries, and the machine learning. And in this way, you get an answer directly for the science report, which is a very high confident answer that what you could get in the samples. And in this way, we can really enhance and use these tools to support the field activities and the choice of the sample. Of course, this would be much more problematic if you would have just the data, the raw data, to analyze. It will require a lot of time for the science backroom, and it will be really not really useful. Anyhow, we will always have the raw data to be analyzed afterwards for more precise scientific outcomes. Thank you.
All right, thank you.